Hello everyone, welcome to Adam. So now we will solve this question based on Otto cycle, where we have been given the initial condition, the compression ratio and the heat supply. And here we have to find the maximum pressure and temperature and the cycle efficiency. So if you draw in the ideal cycle Otto cycle diagram, you have something like this where 1, 2, 3, 4 are the points and 1, 2, 2, 3, 2, 3, 2, 4 and 4 to 1 are the processes. So this is a PV diagram, and 1 to 2 is the isentropic compression process. 4 to 1 is the heat rejection process. 2 to 3 is where the heat is added to the system, or the Q is supplied or the heat is supplied, and 3 to 1 is where the engine will do the work. So this is how this is the composition of a typical diesel cycle, or sorry, the Otto cycle, where also you can observe that the heat addition is being done at constant volume. So this is a constant volume heat addition process. So we have to calculate the maximum pressure first, and the maximum temperature, and the cycle efficiency. So let us see how we can do it. And now if you observe from the cycle, it is obvious that pressure will be maximum at 0.3. But what about the temperature? So temperature will be maximum also at 0.3, because 2 to 3 is an heat addition process. So whatever the temperature will be at 0.2 after the compression, it will still be like lower than the 0.3, because then the heat will be added at 0.2 and then it will rise to something at 0.3. So that is why temperature will be also maximum at 0.3. So by first solving this question, we need to write the initial conditions which we have, which is pressure at 1 is 0.1 megapascal. We also have temperature at 1 as a 35 degrees Celsius, which you need to convert into Kelvin. So 273 plus 35 will be 308 Kelvin. The compression ratio is 9, and the heat supplied, which is Q, is 1800 kilojoule per kg. And the value of gamma, if it is an air cycle, it should be 1.4. And the value of, because this is a constant volume heat addition process, so the volume of CV should be 0.72 kilojoule per kg Kelvin. So this is for air, and it is the value of CV. So you can check this also. It should be 0.72. And for the maximum pressure and temperature of the cycle, first we need to calculate the temperature at 0.2, and then using the heat addition between 0.2 and 3, we will calculate temperature at 0.3 also. So let us see how we can do that. Firstly, we have a PV to the power gamma is equal to constant for the process between 1 to 2, because it is an isentropic compression process. So you can just convert this P into the terms of T using the ideal gas equation, which is RT by V. V to the power gamma is constant. You have T V to the power gamma minus 1 is constant, which will be T1 V1 to the power gamma minus 1 is put to T2 V2 to the power gamma minus 1. So you can easily calculate T2 from T1 into V1 by V2 will become the compression ratio, because V1 is volume before the compression, and V1 V2 is the volume after the compression. So it will be the compression ratio. So it comes out to be T1, which is 308. R is 9 to the power 0.4. Should come out to be 741.7 Kelvin. Let us just type it here, though on the terms which we get. So T2 is 741.7 Kelvin. So after this, you can solve for T3 very easily, because you know that for constant volume heat addition process, you can write the heat supplied, which is given in the question, as Cp delta T, when the units are in kilojoule per kg. So Qs is given in kilojoule per kg as 1800. And Cp, you know, this is Cv, sorry, not Cp. Cv is for constant pressure, and Cv is for constant volume. And because this is an Otto cycle, it should be constant volume heat addition. So Cv should be 0.72, and delta T should be T3 minus T2, which we have calculated as T 741.7 Kelvin. And if you calculate this, you will get T3 as 3248.66. So let us just write T3 as 3248.66. Further, we need to also calculate the pressure at point 3. So for that, we first need to calculate the pressure at point 2, which will again be using this isentropic compression equation. P1, V1 to the power gamma should be equal to P2, V2 to the power gamma. So P2 will be equal to P1 into compression rate to the power gamma. And the pressure at point 1 is 0.1, 9 to the power 1.4 because gamma is 1.4. So it will come out to be 2.167 megapascal. So P2 come out to be 2.167 megapascal. And if you observe the process 2 to 3, you will get it as a constant volume process. So for a constant volume process, you can always write the PV is equal to RT as the ideal gas equation. And for a constant volume process, the RT by P should be equal to also the constant. So RT by P for 2 should be equal to RT by P for the point 3, because 2 to 3 is a constant volume process. So you have a T3 by T2 as a P3 by P2. From there, you can calculate P3 value as P2 into T3 by T2. And P3 from there will come out to be 9.5 megapascal. So P3 will come out to be 9.5 megapascal. Further, we have found out the maximum temperature and pressure. Further, we need to calculate the cycle efficiency. This is an Otto cycle. For an Otto cycle, the efficiency is simply written as 1 minus 1 to the 1 divided by r to the power gamma minus 1. Which if you put the gamma value as 1.4 and r value as 9, you can easily calculate it as 58.5% as the cycle efficiency. So this is how you can solve this simple question based on Otto cycle. Thank you.